Okay, so Taylor's theorem. If fx has derivatives of all orders, so in other words, we can keep differentiating fx on the interval I, where it's defined, and which contains the value of a, then fx equals the Taylor series plus the error. That's what that says there. It's the Taylor series plus the error for x is in I. So it's the Taylor series that approximates it plus any error that we've forgotten, which is generally the next term. Do you remember that? For n plus 1. Which equals n is 0 to infinity. Now look at this. It seems like the error's gone all of a sudden, but it works if the limit as n approaches infinity of the error is 0. So if the error approaches 0 as n approaches infinity, that's okay because we're not adding anything really anyway. And where the error is the n plus 1th term, and we put c in there, if you remember, for some constant c between x and a, where c depends on x. Taylor's theorem tells us that the Taylor series of a function f does not necessarily converge, but when it does converge, it equals fx if and only if the error approaches 0 as n approaches infinity. This makes sense since if the error approaches 0, the sum must approach a finite number. In other words, the terms themselves are approaching 0 then. Does that make sense? Because r is like the next term. So if the terms are approaching 0, the sum of them should approach a limit. They should be bounded. Addition of series. Suppose the ANXN has a radius of convergence RA. So between certain x values in R, it converges. And BN1 has a radius of convergence of RB. Then the sum of the two series, AN plus BN, which can be rewritten as that there with x to the n taken out, has a radius of convergence of the minimum of RA and RB, in other words, like the smallest one, which makes sense because, for instance, if RB is smaller, RB only converges, this one B converges for RB, then the whole thing is only going to converge for the smaller one, which is RB. Question 1, show that fx equals cos x is equal to its Maclaurin series expansion. Wait a minute. If it equals the Maclaurin series expansion, what must be true? Oh yeah, a is 0 for Maclaurin, that's right. But also, if it's equal to the series expansion, this bit is the error, the limit as n approaches infinity of Rn or whatever it is, should equal 0. So, if we want to show that it equals, we need to show that limit. And then find the radius of convergence. Okay. What is this Maclaurin series for cos x? So, the Maclaurin series is, or Tn, I should say, is the sum as n equals 0 to infinity of, now, the derivative, so it's the nth derivative. So the nth derivative of, what's a? So I put that 0 times, it's just x to the n over n factorial. So let's have a go. First of all, let's do some derivatives. So fx is cos x. Maybe on the side. What's f dash x? Sine x. What's f double dash x? Negative sine x, which then is negative cos x. F triple dash x? Yes. And so forth. We'll do one more just to see kind of the pattern. Oh, what's that? The fourth derivative. Beautiful. And now we repeat. Something to think about. Okay, so now let's put that in. So for the first one, when n is 0, what would the first bit be? Cos of 0, and then n is 0, girls, so then x to the 0, which is 1, and 0 in factorial, which is 1. Plus, when n is 1, what do we get? Negative sine 0, and then x to the over 1 factorial. It's n factorial. Plus, when n is 2. Yep. Oops, whoa, 0. Then, yep, then. Okay, let's do a few more because I want to see a pattern. Sorry, I'm going to go down here. Third, when n is 3. Here, yes, sine 0. Beautiful. Plus, one more. Cos of, yep, that's right. Beautiful. Plus dot, dot, dot. And then let's have a look what we get. What's cos of 0? What's sine of 0? So that all becomes 0, which is nice. What the next one? Negative cos of 0. 1, negative 1 times x squared, which is just negative x squared, over 2 factorial, so it's negative. Oh, beautiful. And then what is sine 0 again? And then? Good. I'm going to leave it as 4 factorial because I want you to notice something. Girls, what's the next term going to be?
0.
What's the next term after that going to be? Minus, yes, you're right. Oh, sorry, yeah, minus over. Okay, do you see a pattern? Yeah. So, we've got 1 minus x squared over technically 2 factorial plus x to the 4 over 4 factorial plus, or minus, sorry, x to the 6 over 6 factorial. So, girls, what I want you to notice, first of all, our n values are going up by 2. So you could think of n as being like 2k. Do you get what I'm saying? Where we're substituting then k so that it's always a even number. So like, for instance, our last term could be considered as x to the 2k over what? Yeah, beautiful. So then, but wait a minute, we don't know if the error is approaching 0 yet. What's an expression for the error? What, using this. Using what we've just realised.
X 2k plus 1.
Yep.
Over 2k plus 1 factorial.
Technically this is wrong. 2k plus 1, it's only adding 1. Which should be what also? Sine of, now we actually let it be c. Remember the c term in the r value? So that's rn, I might write down. That's r2k, where we've got x to 0. So what do I actually want to show? So the limit as n approaches, or k approaches infinity if you like. Sorry, should I make it k to keep it in terms of k? Of r2k x to 0 becomes the limit as k approaches infinity, of sine c times x to the 2k plus 1 over 2k plus 1 factorial. That sine c is annoying. Sine c is between negative 1 and 1, so therefore this limit is less than or equal to if we substitute 1 for it, the highest bound. Does that make sense? But that actually approaches 0 since the limit as n approaches infinity of x to the n over n factorial equals 0. And this was previously, shown using ratio test in lesson 18. But I won't write lesson 18 now. But the point is, you could now show it in a test using the ratio test. Okay, so therefore, now girls, is this true for all x? Yeah, it is. This is true for all x. Therefore, cos x equals this. girls, look at back here. How can I write a nice, simple way? Focus on these terms here. The one thing we haven't catered for is the alternating negative, positive. So it goes positive, then negative, then positive, then negative, then positive. How can I show that in my final series?
-1 to the n.
Let's think about it. Let's make it to the n and see if that works. So when n is 0, it's positive. When n is 1, it's negative. And then put the x to the 2n. Let's just think about that for a moment. Everyone overthink, does that work? Take a moment. When n is 0, when n is 1, I get 2 factorial on the bottom, x squared on the top, and a negative. It works. Is everyone with me? So that we can now say cos x equals this series for all x in R. And because it's for all x in R, we say the radius of convergence is, B. Hence, find the Maclaurin Series expansion for the following, including their radius of convergence. So now let's do number 2, which was sine of x. Now, girls, what's the relationship between sine of x and cos of x? Derivatives. So would you say sine of x is equal to not just, not just the derivative of cos x, but then the negative of the derivative of cos x, right? Is everything okay? So in theory, sine x should equal negative the derivative of the series for cos x, right? So which was the derivative of this series, -1 to the n over x to the 2n over 2n factorial. Does that make sense? Which is quite nice, isn't it? Negative. What is our new sum then? We're just differentiating, so what are we going to do? -1 to the n, 2n times x to the -1 over 2n factorial. That's okay, it's all good. Have a look here and here. Anything you notice? Yes, so if I cancel this with the 2n in there, what's actually left on the bottom?
2n minus 1.
Nice. And then on the top, it's just this. That technically can't be our answer, even though it is the derivative. Take a moment and think about why. I'll give you a clue.
Oh, it has to be 1, doesn't it?
I think that's what we learned in that previous lesson. When you differentiate, it doesn't work for 0. So check that if you forget. So it equals 1 from -1 to the n, x to the 2n minus 1.
Bring that 1 in when you first differentiate up on the third line.
Sorry, what?
Do you bring that 1 in when you first differentiate it on the third line?
Bring what 1 in?
That n equals 1.
Oh yeah, I should have put it here and here. We only just realized it.
Yeah.
Now, I still don't like it. We're almost there. Girls, I want the whole thing in the series. What's not in the series yet? The negative. Let's put that in.
That's fair.
So the only thing that changes in the series would be, take a moment, think about it. The x is fine. The bottom is also fine. If I times that by another -1, what does it become? -1 to the?
N plus 1.
Yes. We're just timesing it by another base, therefore we add 1 to the power. That's all it is. And that is our answer. Similar to the other ones, would the radius of convergence be infinity? So let's write something like similarly. Radius of convergence is infinite. Number 2, let fx equal ln 1 plus x. A, part 1. Find the Maclaurin series for fx and its associated interval of convergence. So I'm like, oh God, I don't know where to start. Let's just write down the, what's the general term, the general TNX. So how does it go again for a Maclaurin? Okay, so let's do what we've been doing. N is 0 to infinity of the nth derivative when A is, because of Maclaurin series, yep, of x to the over, beautiful. Okay, so let's put it in there. Now, this is my advice. Before we get into it, let's actually find some derivatives. Do I need to wait?
Well, these are not going to be fun.
Okay, so, girls, let's find some derivatives. First of all, fx is ln 1 plus x. What was that? 1 plus x. What's f dash x? What's f double dash x? Ooh. Not as hard as it looks. Good, because we rewrite this as x plus 1 to the negative 1 to differentiate it again. And then that becomes negative x plus 1 to the negative 2, which equals negative 1 over x plus 1 squared. All right, so f triple dash x. Positive 2.
Times x plus 1 to the negative 3.
Sorry, I should have,
That's right.
You're right, I'll rewrite that because it might help. Okay, f the fourth derivative. There's a reason I'm doing so many. Just thoughts?
Negative 6
Mm-hmm.
over x plus 1.
Beautiful. And the fifth derivative, and I'll stop there. Well, it's 24, or in other words, 4 factorial
She just flexed so hard.
to the 5. So now, Natalia noticed this is actually 4 factorial over x plus 1 to the 5. This is, think about that, this is negative, 3 factorial over x plus 1 to the 4. So I'd like you to realise now, wait a minute, this is Maclaurin, so what do I actually want for all of these? F of 0. We're not doing it. The C only comes in for the error bit. We're not doing that. What's f of 0? ln of 1. What's ln of 1? What's f dash of 0? Use the fraction ones, they're easier. 1. What's f double dash of 0? What's f triple dash of 0? 2. What's f fourth derivative of 0? Negative 6. And the fifth derivative? 24. So let's rewrite these now in terms of, so this is when n is 0, this is when n is 1.
It's n minus 1 factorial.
Okay, I think so.
Negative in there, so I don't know.
That's all right, we'll get there one thing at a time. N minus 1 factorial, are we all in agreement of that?
Yeah.
Okay, that'll give us the value. What about the negative? So that's 1 minus 1 factorial, that works. This is 2 minus 1 factorial. 3 minus 1 factorial, yep, that all works. And then it's negative 1 to the...
Minus 1.
Yes. So 1 minus 1 is 0, so it's positive. Negative 1 to the 2 minus 1 is negative, that's good. 3 minus 1, negative 1 to the 3 minus 1, this is terrible. Anyway, so after doing all that, we realize the nth derivative where x is 0 is, what's the formula? And you've already pretty much said it. Yes? To the n minus 1. Good. So, after all that, therefore, the Maclaurin series is of, what was it? ln 1 plus x equals the sum from n is 0 to infinity of negative 1 to the n minus 1, factorial, times n minus 1 factorial times, what's the next part? X to the n over n factorial, but we can simplify that. What happens then? What can we do? And n on the bottom. And then we've got negative 1 to the n minus 1 over x to the n.
When is it convergent?
Yeah. How do I do that?
We do a ratio.
We could do a ratio. Oh, yes, all alternate thingamajiggies.
Isn't that similar to the ratio?
It is probably similar, which is probably good. You can do either one. Do you want to use the ratio test? So the limit, as n approaches infinity, of an plus 1 would be negative 1 to the n. So girls, I got absolute value of x is less than 1.
Yes.
Yep, so what do we also need to check? The endpoints, remember? Because when it equals 1, we don't know anything. So let's think about that for a second. When x is negative 1, let's just think about fx for a second. What does fx become? ln of negative 1 plus 1, which is ln of 0. What's ln of 0?
1.
No.
Oh, no.
It's undefined. Therefore, x cannot equal negative 1. So, what about when x is 1? When x is 1, now when x is 1, fx is fine, so that doesn't help me. But the actual series that we found when x is 1, which is, this one up here, becomes Tn of 1, which becomes the sum n equals 0 to infinity of negative 1 to the n minus 1 over n, because x is 1. Now, I believe this is convergent according to the alternate series test. And you can look that up. Converges by alt series test. So therefore, what is my interval? And? Beautiful, because we said it converges for that. Now let me just... So girls, remember, I just want to point out, this is the Maclaurin series. So we've done that bit. And then down here is the interval of convergence.